Hello, dear students, and welcome to this week. So this is a lecture about this week's chapter, object-based image analysis. Object-based image analysis is actually based on traditional pixel-based classification. So you actually classify the pixels, but then you allocate the pixels into kind of objects. So it augments the pixel-based analysis with additional information, like some kind of sort of perception information. It is a two-step approach. So the first step, you segment the image, you create objects, um, and then the second step, so the objects, the computer doesn't know if they're related to each other or not, it just generates objects. And the second step will be that you classify the objects. So it's almost like a double clustering. So you first cluster each pixel into these objects, and then you cluster the objects into what we will call landscape features. And the classification can be used, we can use a supervised or unsupervised classification like you did last week. So you've learned about supervised and unsupervised classifications last week, so we won't go into detail here, but basically now we generate objects, and the objects are also then classified. So two steps. The segmentation algorithms, there's many of them, and typically they create clusters of pixels by using not just the spectral information of the pixel, but using contextual information, like the texture of the surrounding pixels, or the color of the surrounding pixels, or the value. But also we can determine and limit what kind of shape we want our objects to be, what type of size we want it to be. So like this, we add additional information and context to the classification of the pixels. The process that we do in this week's chapter is called SNIC. SNIC stands for simple non-iterative clustering. So it's non-iterative because a lot of segmentation processes, they iterate through different stages of the segmentation to find the best possible segmentation. SNIC is non-iterative; it just generates one segmentation. It is bottom-up, meaning it starts from the data itself, and it is seed-based. So you generate a grid, and then the objects they start from these grid points. And then in SNIC, we can control for compactness, connectivity, and neighborhood size. And we'll have a look at those parameters in a second. So basically, the way SNIC works is that you have a raster that you want to classify. So the raster has pixels. And the first step is to generate the seeds that we're going to call superpixels. So we generate an equally spaced grid. So we determine that based on the size. We'll look at it in a second. But basically, we just have points equally spaced, and those points they fall on a pixel, and this is what we call our superpixel. Our superpixel has a value. For simplicity, we're just going to use one value here. It can be 13, 2, 5, 20, so it can be any value. But actually in the Google Earth engine, it actually generates, it can use multiple bands. So you not just have one value, but you have multiple values for the different bands. Okay, now we have pixels with the superpixels with a value. And now what we have to do is to start classifying or allocating or clustering the surrounding pixels to one of the superpixels. So basically, all the pixels have a value or multiple values because of multiple bands. But in this case, let's look at just at one value. And basically, let me see if I can write with my pen. Yeah. And basically, this is my superpixel. And then it looks into the surrounding pixels. Okay, this is 1. Then it looks at spectral similarity and spatial proximity. In spectral similarity, we'll look if the value on my pixel, is it similar to the superpixel or not? And it can use multiple bands for that. So you generate this kind of a similarity index, trying to allocate it. The other one he will try to do is spatial proximity. He will look if a certain value is very close by. He will have a kind of a weight to be allocated to the superpixel. Or if this weight of the spatial proximity is not so important, the spatial proximity, then even if a certain pixel is very close to a superpixel, if it's very similar to another one, it will be allocated to this other one. Okay, so it starts from the superpixel, then it looks at the surroundings based on connectivity. Is it similar or not? And then you go to the next one, then to the next one, to the next one. It's kind of a growing algorithm. Okay, so now we understand how it works a little bit. And basically, so it will then just cluster the pixels into one object. In this case, two objects. So let's call it the green and the orange object. And if you have now every superpixel will generate one object. So this one here on the top that we just see now, it's the same story. So because this, like this number one is equally similar to this superpixel and to that superpixel, it will take into account the spatial proximity and then will be allocated to that one. And this same story. So it takes both spatial proximity and spectral similarity. And it will generate yet another object. But as you can see, although these are two different objects, this is one object, and this is a different object. So the computer doesn't know that they are the same. So even though we can see they're very similar, it will just generate different objects for them. That's why we need a second step approach. Again, a clustering algorithm that will now cluster the objects instead of the pixels. So what it does, we do it again, either supervised or unsupervised classification, and we're going to cluster the different objects and say, okay, oh, this is very similar. This one object is very similar to that one. So they will then be clustered into one landscape feature, let's say. So this becomes, if you do it a supervised classification, you can say, well, this is water, this is bare soil. Then you generate all the objects that are water, they come together, and the objects that are bare soil, they stay together. Yeah, so the two-step approach. Now let's have a look at the different parameters we can choose for SNIC. We can only choose size, compactness, and connectivity. And let's start with connectivity. And the connectivity, as the name implies, basically is the way the cells are connected to each other. And you can only choose from connectivity 4 or connectivity 8. And it's very intuitive. So if you have this cell, if you have connectivity 4, you can only attach to these 4 different cells. So 1, 2, 3, 4. And if you choose connectivity 8, you can choose 1, 2, 3, 4, 5, 6, 7, 8. So 8 different cells. So of course, connectivity of 8, it costs a bit more processing power. Is for every pixel. For every pixel, you'll have to check the 8 surrounding cells if they belong to it or not. But connectivity 8 usually delivers more smooth, more natural shapes. So if you're looking for like a natural features, definitely use connectivity 8. If you're looking more for like man-made features, more like squarey, maybe connectivity 4 will make more sense. So like if you're looking for, I don't know, swimming pools or solar panels, maybe will make more sense. But in general, 8 delivers more smooth, more natural features. Okay, that was the connectivity. I think I even have an example here. So imagine that you have this pixel over here. If you allow connectivity of 8, it can connect like this. So this one will belong to this object. And if you don't allow connectivity of 8, just connectivity of 4, it will then only be able to connect like this or like this. So then you have a different type of shape. Okay, so we're controlling a bit for shape. The other thing we can do is control for size. And size is dictated by the superpixel size. So very simply put, it is the distance between the seeds, the superpixels. So now we're looking at this example. So we have a kind of distance between the seeds, but this is the same more or less how on average how big the objects become. So if you would say, okay, I don't care about spectral connectivity, spectral similarity at the moment. So in terms, so my size will then generate, it will generate objects more or less like this. So equally spaced. So on average, this will be the size of the objects. Okay, let's have a look, for example. So imagine that you have double the size, so you have less superpixels. And then while before you had this kind of size of objects, right? With the new with the new size, a larger size, then of course they will become bigger objects. So you have to take that into account when you're trying to classify, for example, swimming pools or lakes or cities. This size will be important in understanding what kind of minimum size of objects you're able to classify. So although there is a minimum size of objects because of this superpixel size, the maximum size of objects doesn't really matter, because even if you generate objects, several objects, they can be clustered together into one landscape feature. So you will not determine a maximum size. Okay, so we've discussed connectivity and size, and the next one is compactness. Compactness also relates to the shape of the objects, and basically, compactness tells about the kind of shape that is allowed. So, in terms of it deals with the weight you give to the spatial proximity that we just discussed. So compactness actually is a metric that relates the perimeter. Let's draw it here. So this will be the perimeter of a shape. It's kind of meters, let's say. It relates the perimeter against the area of a shape, which is square meters. So, for example, a circle is a very compact shape because it has the smallest perimeter for the maximum area. And in a square and a hexagon, they're all very compact shapes. And then when you start having these kind of shapes, so elongated, so with a very large perimeter for the same amount of area, then you are less compact. Okay, so as an example, so if you determine a very high value for compactness, then you generate something like this. So that you give a lot of importance to the spatial proximity. So all the cells that are close by will probably be then allocated to that object, to that superpixel. While if you lower the compactness, you're then going to give more importance to the spectral similarity. So even an object that is very far away, if it is similar to this superpixel, will still be allocated to this superpixel. So you generate different types of shapes because of this. Okay, so I think these are the three parameters that I wanted to take to discuss. And let's have a look now. So based on this, we can better understand what we want to choose, and we can better understand the results that we're having. And I'm not going to go through all the code like from the book, but I wanted to go through the results so that you understand a bit what the results mean. But because the code is very well explained in the book. Okay, let's have a look at the results. So let's have a look at our results. First, we see the image with the infrared bands. Yeah. If you zoom out, you see the whole image. But there's many other nicer layers. You normalize the image, not so interesting. This one gets interesting here. So, of course, these are the seeds. So the distance the size that we used is related to the distance between the points. So I think we use 16. So if you actually count all the pixels, you will count between 2 points, it's a half of the size. So you count like 1, 2, 3, 4, 5, 6, 7, 8. That means 16 will be your superpixel size. So that was interesting to see. So of course you can't, if you're looking for a swimming pool, it's related to the size of the areas that you want to find. Then on top of that, we can see actually the segments that the process created. This is also very interesting to observe. So it's spectacular to see these random colors at play. But here we can very nicely observe, for example, here that the spatial aspect, the compactness is very low, is 0, so it doesn't care. So it can go very far from its superpixel, even beyond the other pixels. So if you would have a higher value of compactness, you have more of these kind of shapes where all the pixels are around the value. Next one, interesting to have a look at. Well, it was a nice one, a nice visualization where they colored the segments based on the average of the segments. So we have a better feeling of what's going on each one of the segments. But the nicest one is at the end, where we can have a look at the normal pixel-based classification. So you have a lot of noise, speckles, as we call it. So just pixels being classified a different class, and using indeed our object-based approach, you have then a much cleaner, much more defined objects. Okay, so the size of the objects, again, it depends on the parameters you choose. So it depends on what you're looking for. If you're looking for burned areas, or if you're looking for lakes, or for like, for example, cities or shape of cities, you will then be able to decide that based here. Yeah, I hope you enjoyed this chapter, and I'll see you soon.